ever switched optimizers from SGD to Adam and watched your loss suddenly drop twice as fast? Today, we're breaking down optimizers, the algorithms that decide not just which direction to nudge the weights, but exactly how far, how fast, and how to adapt that step over time. You already know that backpropagation gives you the gradient, the direction that increases the loss. An optimizer flips that sign and moves the weights in the opposite direction. But the naive version of that idea has two serious problems. First, every weight gets updated by the same step size regardless of how often that weight actually gets useful gradient signal. Second, mini-batch gradients are noisy estimates, not exact values. And pure gradient descent will zigzag and oscillate instead of heading cleanly toward the minimum. The base update rule is theta gets replaced by theta minus the learning rate times the gradient. That's vanilla gradient descent. Every optimizer you'll ever use is a refinement of exactly this one line. SGD, stochastic gradient descent, uses one random sample or a small mini batch per update instead of the full dataset. That makes it dramatically faster, but the gradient estimates are noisy, and the path to the minimum looks like a zigzag instead of a straight line. In practice, mini batch sizes between 32 and 256 balance speed and stability well. The noise isn't purely a weakness. It acts as implicit regularization and helps the model escape shallow local minima. Momentum fixes the zigzag problem. Instead of using the raw gradient each step, it maintains a running average called the velocity. Think of it like a ball rolling downhill. It builds up speed in consistent directions and dampens oscillations from noisy gradients. The momentum coefficient beta, typically 0.9, controls how much of the previous velocity to carry forward. The result is a much smoother, faster path to the minimum. AdaGrad takes a different approach. Instead of adapting direction, it adapts the learning rate per parameter. It accumulates the squared gradients over all past steps, then divides the learning rate by the square root of that accumulation. Rare features. Ones that get infrequent gradient updates automatically receive larger steps. Common features get smaller steps. This works beautifully for sparse data like text. The fatal flaw, the accumulation only ever grows, so the learning rate shrinks towards zero and training eventually stalls. RMSProp fixes that. Instead of summing all squared gradients, it uses an exponential moving average, a forgetting factor root that discounts old gradients and keeps only recent history. The accumulation stays bounded, the learning rate stays alive, and the per-parameter adaptivity is preserved. RMSProp was the standard choice for recurrent networks before Adam took over. Adam combines all three ideas: the momentum term from SGD with momentum, the adaptive per-parameter rates from RMSProp, plus one critical addition: bias correction. Early in training, both moving averages start at 0 and are artificially small. Adam divides by 1 minus beta to the power t, correcting this bias and preventing wildly large updates in the first few steps. The defaults: beta 1 equals 0.9, beta 2 equals 0.999, epsilon equals 1e8, learning rate equals 0.0001. Work well across an enormous range of tasks and architectures. Adam is the starting point for almost every deep learning project today. But Adam isn't always the winner. SGD with momentum and a carefully tuned cosine annealing schedule frequently outperforms Adam on image classification tasks, producing models that generalize better. Watch the comparison. Adam reaches the minimum in fewer steps, but SGD with the right schedule can land in a flatter, more generalizable region. For transformers, adamw with warm-up is the standard. And always pair any optimizer with a learning rate schedule because a fixed rate is almost never optimal. Thanks for watching. If this helped, like, follow, and subscribe.